Hi all, good morning. So today I am going to take a class on module 4 circular slabs. So you all heard about slabs, normal conventional slabs, that is one way as well as two way slabs. So how will you differentiate one way and two way slab? So we have already seen that in last semester. So one way slabs are the slabs on which the Ly by Lx ratio is greater than or equal to 2, whereas two way slabs are the slabs where Ly by Lx ratio is less than or equal to 2. Right. So we all know about the bending or deflection criteria of this one way as well as two way slabs, and we have we have designed and detailed this one way as well as two way slabs. So now we can move on to the circular slabs. So can you please tell me where we can see these circular slabs? So the circular slabs are used in the following purposes, like so we can see circular slabs above the circular rooms, that is the roof of circular rooms. And also we can see circular slabs at the base as well as roof of circular water tanks, and also over the wells, and also we can see circular slabs at the roof and floor of traffic control post at the intersections of roads. Okay, and now we can go for the bending criteria of this circular slabs. See, the bending of a circular slab is quite different from that of a normal conventional slab. So everyone know that this normal conventional slab bent in a perpendicular direction with respect to the loading. So what happened to the circular slab is that when it is subjected to a uniformly distributed load, a circular slab bent in a mutually perpendicular way in the form of a saucer, or it deflect in the form of a saucer, and because of this it develop both radial as well as circumferential stresses. So this tensile stresses, which is both radial as well as circumferential in nature, develop on the convex surface of the circular slab, and the compressive stresses develop on the concave surface of the deflected circular slab. So normally we have to create or we have to provide reinforcements both at the center as well as on the edge of the circular slab. So because of the development of tensile stresses, that is both radial as well as circumferential stresses on the convex side of the slab, this reinforcement is required both in the radial as well as in the circumferential directions at the convex surface of the slab. So this arrangement of reinforcement will create a lot of congestion at the center of the slab. Hence we have to make an alternate arrangement to avoid this congestion of reinforcement. So here we are going to provide a reinforcement near the center of the circular slab in the form of a mesh, that is in mutually perpendicular directions. The reinforcements are provided near the center of the circular slab, and also towards the edges of the circular slab the reinforcements are provided both in the radial and circumferential reinforcements. These reinforcements are provided at the edges for taking the negative reinforcement which is coming at the support. So therefore near the edges of the circular slab the reinforcement is provided in the radial and circumferential directions. And now we can move on to the analysis of a simply supported circular slab. See, normally the analysis of a circular slab can be considered to be of three types. So that is, the first case is simply supported circular slab, and the second one is fixed circular slab, and the third one is semi-fixed circular slab. So we can see, first we can see about a simply supported circular slab. So the figure shows a simply supported circular slab So a simply supported circular slab which is subjected to a uniformly distributed load of W per meter square. So this slab will generate two types of bending moments. The first one is the bending moment in the radial direction, and the second one is the bending moment in the circumferential direction. Therefore, we have two types of bending moment diagrams, that is MR diagram as well as M theta diagram. So MR represents the radial moment diagram, and M theta represents the circumferential moment diagram. Okay, so here we have to learn by heart this following equations. That is, so this circular slab which is having a radius capital R, and this radius is capital R, which is from the center towards the edge of the slab. So consider a point P, so which is located at a point from the center of the circular slab, that is O, at a distance of small r. And now we can find out what is the radial moment at the center. So radial moment MR is given by the equation 3W by 16 into capital R square minus small r square. So the radial moment, once again I am telling, the radial moment MR equal to 3W divided by 16 into R square minus small r square, as well as the circumferential moment. Circumferential moment is represented by M theta. So M theta it will be equal to W by 16 into 3 capital R square minus small r square. This is at a distance of small r from the center of the slab. That is MR equal to 3W by 16 capital R square minus small r square, and M theta equal to W by 16 3R square minus small r square. So when the center of the circular slab small r equal to 0, that is at the center your r will be equal to 0, right? Then what about this MR and M theta? Here MR will be equal to M theta. MR will be equal to M theta will be equal to 3W R square divided by 16, because here small r will be getting 0, right? So that is at the center of the slab your small r will be equal to 0. Therefore, in the previous equation you have to substitute for r, you just substitute it with 0. Therefore, your equation will be equal to MR equal to M theta equal to 3W capital R square divided by 16. So at the center of the circular slab, when r equal to 0, your MR equal to your M theta equal to 3W capital R square divided by 16. And now we can see at the support what will happen to this MR and M theta. That is, towards the support what will happen to your small r? The small r will be equal to capital R, right? So the small r equal to capital R at the support of the circular slab. Therefore, what will happen to your MR? Your MR will be equal to 0, and M theta will be equal to 2W R square divided by 16. So these three equations you need to learn by heart. Once again I will tell, that is at a distance small r to any point P from the center of the slab, the radial moment will be equal to 3W divided by 16 into capital R square minus small r square, and the circumferential moment will be equal to W by 16 into 3 capital R square minus small r square. And at the center of the circular slab, when small r equal to 0, MR equal to M theta equal to 3W R square divided by 16, and at R equal to capital R, that is at the support of the circular slab, your MR will be equal to 0 and M theta will be equal to 2W capital R square divided by 16. And one more diagram I need to mention here is the shear force diagram. Okay, so this shear force diagram we can see In the shear force, we have got an equation which is equal to W into capital R. So where is actually the maximum shear force will be coming? The maximum shear force will be coming at the support, right? So at this support, the maximum shear force will be equal to W into capital R. Fine. So these three equations you please learn by heart. Then only we can do the next problem. Thank you.